What are galaxies and why do they matter? Imagine looking up into a perfectly dark sky. What appears as a misty cloud in a telescope might actually be a galaxy. A massive collection of stars, gas, dust, and dark matter bound together by gravity. Our own galaxy, the Milky Way, contains over 100 billion stars. But it is just one of an estimated 1 trillion galaxies in the observable universe. So what exactly is a galaxy? In essence, a galaxy is a gravitationally bound system. It can range from a few million stars to trillions. These stars orbit a common center, typically dominated by a massive concentration of mass, often a supermassive black hole. Galaxies are the structural building blocks of the universe. They are where stars are born, evolve, and die. They host planets and potentially life. Their dynamics and distribution reveal how the universe formed and evolved from the Big Bang to today. The study of galaxies is not merely an exercise in classification. Understanding how galaxies form and change tells us how the universe itself changes over cosmic time. It is like reading the universe's autobiography, chapter by chapter. One of the first to attempt this cosmic classification was Edwin Hubble. In the 1920s and 30s, Hubble used the Mount Wilson Observatory's powerful telescopes to identify and categorize galaxies. His now iconic tuning fork diagram remains a cornerstone of galactic astronomy. Hubble's diagram splits galaxies into 4 main categories: spiral, elliptical, lenticular, and irregular. These shapes are not just aesthetic variations. They hint at the past and future of a galaxy. How it formed, how it interacts with its environment, and how it might eventually die. In the following parts of this video, we will take a tour through each of these galactic types, how they differ, what they contain, how they behave, and then dive into the processes that allow galaxies to evolve, merge, and even completely transform. From swirling spirals to ancient ellipses, from chaotic irregulars to the transitional lenticulars, the universe has built a breathtakingly diverse gallery of galaxies, and the best part, we're still discovering new ones every day. Among the many shapes galaxies take, spiral galaxies are perhaps the most iconic, with their sweeping arms and luminous cores. They are both scientifically fascinating and visually stunning. Spiral galaxies are characterized by a flat, rotating disk that contains stars, gas, and dust, along with a central bulge of older stars. Radiating from this bulge are spiral arms, regions of enhanced star formation, where new stars are constantly being born. There are 2 main subtypes: normal spirals designated as S-barred spirals SB, which have a central bar-shaped structure of stars extending from the nucleus, with arms spiraling outward from the ends of the bar. Our own galaxy, the Milky Way, is a barred spiral galaxy. Another famous example is the Andromeda Galaxy M31, our nearest large galactic neighbor. But what gives spiral galaxies their distinctive shape? The prevailing explanation involves density wave theory, first proposed in the 1960s by C.C. Lin and Frank Hsu. According to this model, spiral arms are not rigid structures but rather waves of increased density that move through the disk. As gas clouds enter these waves, they compress and trigger bursts of star formation. The bright, young, blue stars that form make the arms stand out, though they live short lives and die in spectacular supernovae. Spiral galaxies are typically rich in cold gas and dust, making them active sites of ongoing star formation. They tend to have high angular momentum, meaning they spin fast. Disk-like structure with clear rotation patterns, younger stellar populations than ellipticals. Prominent dust lanes visible even in optical images. This youthful, energetic nature makes spirals a cosmic laboratory for studying star birth and stellar evolution. Observations from instruments like the Hubble Space Telescope and ALMA have revealed intricate details of these galaxies. For example, the Whirlpool Galaxy M51 shows clear evidence of gravitational interaction with a smaller companion galaxy, which may be enhancing its spiral structure, a process sometimes referred to as tidal triggering. Despite their order and symmetry, spiral galaxies are not static. Over time, interactions with other galaxies, or loss of gas, can cause them to evolve into different shapes, a concept we'll return to in Part 5. Spiral galaxies dominate the local universe, especially in low-density environments like the edges of galaxy clusters or in the field. But their future is not guaranteed. Some will collide, merge, or slowly transform into more spheroidal forms. Their structure is a snapshot of cosmic youth and rotation, a moment in a galaxy's dynamic life cycle. If spiral galaxies are the graceful dancers of the cosmos, elliptical galaxies are the old, stoic giants, devoid of spiral arms. They possess a smooth, oval, or spheroidal shape, often featureless, invisible light, but rich with clues to cosmic history. Elliptical galaxies range in size from dwarf ellipticals with just a few million stars to giant ellipticals harboring trillions. They are classified from EO to E7, based on their elongation, EO being nearly spherical, and E7 highly elongated. Unlike spirals, ellipticals show little or no rotation. Stellar motions are mostly random, resembling a three-dimensional swarm. Minimal cold gas and dust. They are often called red and dead because they no longer form new stars. Older stellar populations dominated by yellow and red stars that have long outlived their active star-forming phases. So how did these galaxies form? One of the dominant theories involves galactic mergers. When the spiral galaxies of comparable size collide, a process known as a major merger. The gravitational forces involved can randomize stellar orbits, strip away disks, and destroy spiral structure. What's left is a more isotropic, spheroidally distributed system. In other words, an elliptical galaxy. Computer simulations by researchers such as Joshua Barnes and Lars Hernquist in the 1990s were instrumental in demonstrating how mergers transform disk galaxies into ellipticals. These simulations, running on early supercomputers, showed that within a few billion years, the structure of the merged system settles into a smooth, ellipsoidal form. Observational evidence supports this scenario. Hubble Space Telescope images have captured galaxies in mid-merger, with long tidal tails, multiple cores, and disturbed morphologies. The centers of massive elliptical galaxies often contain supermassive black holes, and their masses correlate with the velocity dispersion of stars, a relation known as the M-sigma relation, discovered by Gebhardt et al. 2000 and Ferraresi and Merritt 2000. This hints at a coevolution of the galaxy and its central black hole. Moreover, elliptical galaxies tend to reside in dense environments, such as the centers of galaxy clusters. Here, frequent interactions and the removal of cold gas via ram pressure stripping make spiral galaxies rare. One of the best-known examples of an elliptical galaxy is N87, located in the Virgo cluster. It gained worldwide fame in 2019, when the Event Horizon Telescope captured the first-ever image of its central black hole, a shadow surrounded by a glowing accretion disk. While ellipticals may lack the visible dynamism of spirals, they represent the mature phase of galaxy evolution, the cosmic aftermath of billions of years of interactions, mergers, and star formation. They are the resting places of galactic matter and history. Not all galaxies follow neat rules. Some defy the tidy categories of spiral and elliptical, either because of violent histories, environmental influences, or transitional evolutionary states. These galaxies, known as irregular and lenticular types, reveal just how dynamic and chaotic the universe can be. Irregular galaxies, galactic chaos in action. Irregular galaxies are, by definition, galaxies that lack a defined shape. They don't have spiral arms. They don't form ellipses. Instead, they're often clumpy, asymmetrical, and full of gas and dust. These galaxies are frequently small and low in mass, but surprisingly active in star formation. The Large and Small Magellanic Clouds, which orbit the Milky Way, are two prime examples. Though once classified as dwarf irregulars, they may now be in transition due to tidal interactions with our galaxy. Irregular galaxies are typically the result of gravitational interactions or close encounters, which distort their structure, gas accretion from intergalactic space, leading to lopsided star-forming regions. Early cosmic conditions, particularly in the high redshift universe where irregulars were more common. Due to high merger rates, NASA's Hubble Space Telescope has captured stunning images of irregular galaxies filled with glowing aged regions, zones of ionized hydrogen around newly born stars, evidence of intense, ongoing star formation. Though often overlooked, irregulars are thought to play a crucial role in galaxy assembly. Some may evolve into more structured types, while others may be fragments from larger mergers or ancient building blocks of modern spirals. Lenticular galaxies SO. The transitional class lenticular galaxies occupy a middle ground between spirals and ellipticals. First categorized by Edwin Hubble as the stem of his tuning fork diagram, they feature a disc-like structure similar to spirals, but no prominent spiral arms, and a central bulge like ellipticals. They are often described as dead spirals, systems that once formed stars actively, but have since exhausted or lost their gas. Key characteristics of SO galaxies: little to no star formation, with older stellar populations, smooth appearance, but with a visible disk in images, low dust content, and a warm interstellar medium. So what transforms a spiral into a lenticular? Several mechanisms are proposed: ram pressure stripping in dense clusters, e.g. Virgo or Coma removes the cold gas from spirals as they plunge through the hot intercluster medium. Galaxy harassment, repeated high-speed encounters, can dynamically heat disks and disrupt spiral structure. Tidal stripping or mergers can also play a role, especially in group environments. Observations from surveys like the Sloan Digital Sky Survey (SDSS) show that SO galaxies are far more common in clusters than in isolation, reinforcing the idea that environment drives morphology. In many ways, lenticular galaxies are the midlife stage of galactic evolution. No longer forming stars, not yet elliptical, but fundamentally transformed from their spiral past. Together, irregular and lenticular galaxies demonstrate the universe's messy, transitional, and sometimes unpredictable nature. They bridge gaps in classification and offer insights into how galaxies grow, suffer, and change, shaped by both internal physics and external forces. Galaxies are not static structures. Over billions of years, they interact, merge, consume, and reshape themselves under the influence of gravity, environment, and internal physics. Understanding galactic evolution means understanding the life stories of the universe's great cities of stars, from spirals to ellipticals, the morphological transformation galaxies can and do. Change type. A spiral galaxy may lose its gas and fade into a lenticular. The spirals may merge into an elliptical. A dwarf irregular might grow through accretion or fall apart from tidal forces. This concept, that galactic morphology is not fixed, is supported by observations and simulations alike. One key process is the galactic merger. A major merger involves galaxies of similar mass. These often destroy ordered rotation, randomize stellar orbits, and produce elliptical galaxies. A minor merger between a large galaxy and a much smaller one may warp spiral arms or create extended gas tails without complete destruction. Simulations from projects like Illustras and Eagle show how galaxies grow hierarchically, small structures merging to form larger ones. These simulations match real data from sky surveys, helping astronomers reconstruct how today's galaxies came to be. Mergers don't just reshape morphology, they also feed the central supermassive black holes, triggering active galactic nuclei (AGN) and massive energy outflows that can regulate or quench star formation. Environmental effects. Galaxies don't evolve alone. Galaxies in dense clusters evolve differently than those in isolation. Processes such as ram pressure stripping, first described by Gunn and Gott in 1972, removes gas from galaxies as they plow through hot intercluster plasma. Galaxy harassment, a term coined by Murad al. 1996, refers to repeated high-speed interactions that destabilize disk galaxies. Strangulation cuts off fresh gas supply, causing star formation to slowly shut down. These mechanisms are most active in rich clusters like Coma and Virgo, where the transformation of spiral galaxies into gaseous O-types is especially pronounced. This shows that galaxies evolve not just due to internal processes, but also because of where they live. The role of dark matter and feedback galaxies form within dark matter halos, massive invisible structures that determine their gravitational potential. These halos are mapped through gravitational lensing and simulations. In addition, feedback mechanisms from stars and black holes regulate galactic evolution. Supernova explosions can drive out flows that remove or heat gas. And feedback from black holes, including radiation and jets, can stop gas from cooling, effectively halting star formation. These processes explain why some massive galaxies stop forming stars earlier than smaller ones, a phenomenon known as downsizing in galaxy evolution. How we know all this? Observing across time. Thanks to telescopes like Hubble and now the James Webb Space Telescope JWST, astronomers can look back in time by observing distant galaxies. Because light takes time to travel, the farther we look, the younger the universe appears. We've observed galaxies forming just a few 100 million years after the Big Bang, small, clumpy, often irregular, radically different from today's mature spirals and ellipticals. These observations allow us to build a timeline. Early universe, irregulars and proto-galaxies dominate. 2 billion years post-Big Bang, massive starbursts, mergers, early spirals. Today, a diversity of types, shaped by billions of years of cosmic evolution. Every deep field image tells a part of this story, from the chaotic youth of galaxies to their quiet maturity. Conclusion: the story of galaxies is the story of the universe. Galaxies are not mere collections of stars. They are the dynamic, evolving, often violent theaters of cosmic history, from elegant spirals to colossal ellipticals, from irregular chaos to lenticular quietude. Their morphologies encode information about dark matter, gravity, star formation, and black hole growth. Their changes are driven by physics, environment, time, and sometimes chance. And as telescopes grow more powerful and simulations more precise, our understanding of galaxy evolution continues to sharpen. The more we learn about them, the more clearly we see our own place in the cosmos, orbiting quietly in a spiral arm of one galaxy among trillions. If you found this video fascinating, give it a thumbs up. It really helps us grow and reach more space-loving minds like yours. And don't forget to subscribe to the channel so you won't miss any upcoming deep dives into the mysteries of the cosmos. Hit the bell icon to get notified whenever we release a new video. We post regularly on galaxies, black holes, space-time, and everything in between. We'd love to hear from you. Which type of galaxy do you find the most intriguing? Spirals, ellipticals, irregulars, or lenticulars? Do you think the Milky Way will one day become an elliptical galaxy? Why or why not? If you could visit any galaxy in the universe, where would you go and why? Let us know your thoughts in the comments below. We read every one of them and love starting cosmic conversations. Thanks for watching, and until next time, stay curious, keep looking up, and never stop exploring the universe.